examples or numerical values of how many sequences of each of these types occurs. Simply having this many ones in a binary sequence of this many terms, this is the number of sequences with the balance property. You should divide this by the period to get the number that are cyclically distinct. This is a huge number, and this would become 2 to the n minus 2 factorial if you took out the single shifts. The number of sequences with the span n property is equal to the number of so-called de Bruijn sequences, and that number is known to be 2 to the 2 to the n minus 1 minus n, all in the exponent, which I can also write as 2 to the power 2 to the n minus 1 divided by 2 to the n. That's an interesting number. De Bruijn and others discovered that this result was first published in the 1890s in a French sort of low-level journal, L'Intermédiaire des Mathématiciens, which was basically a college teacher's journal. Someone had posed as a problem how many such sequences are there, and the same year someone else provided this solution. The argument given in that solution was not very different from the one found about 50 years later by Nicholas de Bruijn. And of course, the number of m sequences, as we observed, is only 5 2 to the n minus 1 over n. So if you sort of take the log to the base 2 of the numerator and of the denominator here, that's an approximation to this number, which tells you that these are very rare among all of the span n sequences. My main conjecture, which I think is certainly capable of disproof by one counterexample, but so far no one has found a counterexample, and maybe it's possible, if it's true, it should be possible to prove it, that if you have a sequence of period 2 to the n minus 1, which has both the span n property and the two-level autocorrelation property, then in fact it has to be an m sequence. It's much harder to search all the span n sequences because their number grows at such a hyper-exponential rate than it is, in some sense, to search all the two-level correlation sequences. But a little bit of problem with searching all the two-level correlation sequences is we're not sure we know what all of them are, other than by exhaustive search. I'll say more about that a little bit later. Now, in terms of weaker combinations of properties, these are the two strongest properties short of m sequences, the span n property and the two-level autocorrelation property. And the evidence we have so far is if you combine those two, the only examples we found are m sequences. But if you have, instead of the span n property, only the run property, and the weaker multiplier property that's weaker than the correlation property, and you have neither the span n nor the autocorrelation, having both of these already occurs at period 31. An unsolved problem is to try to characterize the larger degrees where you can have both the run property and the multiplier property, but not the span n or the two-level correlation property. I'm not sure anyone has even looked very hard. It's not clear that there's any great interest in such examples other than as a mathematical curiosity. It's a little harder to find examples where you have both the span n property and the multiplier property, but without the two-level autocorrelation property. And this already occurs at period 127 or degree 7, and this was found empirically in a search that was done by a former doctoral student of mine, and who searched all of the possible sequences with the multiplier property of period 127 and found that in addition to the 18 M sequences, the 16 M sequences, the 18 M sequences, there were 2 additional ones. And in looking at the data, I realized that this would occur whenever x to the n plus x plus 1 is primitive with a degree n that's odd and greater than 3, and the first such case is n equals 7. So if my earlier conjecture that x to the n plus x plus 1 is primitive for infinitely many n, and in fact if infinitely many of those n are odd, then we would have infinitely many examples of this. What I don't know is whether there are other examples where you have the properties P3 and P4 but not P5, other than arising from this particular structure. Again, I'm not sure that anyone has looked very hard for that, and I don't know what I believe on that. If I believe my main conjecture, then I'm tempted to believe this one also. My main conjecture that if you have span n and 2-level autocorrelation, then it has to be an M sequence. Then I'm tempted to believe that if you relax the 2-level correlation to the multiplier property, the only additional examples we get are from x to the n plus x plus 1 being primitive with odd n greater than 3. The other thing that's slightly weaker than my main conjecture is to have both the run property, P2, and the 2-level autocorrelation property, but without the span n property. And the first known example of this occurs at period 2 to the 7 minus 1, again as that other combination, degree 7 and period 127. And this example was found to occur in one of the 6 families of period 127 identified in Balmert's book. Hal Fredrickson, who was here, helped in the compilation of the tables for that book. And actually the example of the family where this occurs is not the example in Balmert's book, but from a given example, sequence AN, or AI, I should say, if you replace the subscript I by QI, where Q is relatively prime to the period, you get other sequences that we consider equivalent to the starting one. And it was one of the sequences equivalent to an example in Balmert's book that was found to have both the run property and the span n property. And to the best of my knowledge, no one has even identified what was special about that example that led to having these 2 properties. So I'm not sure anyone has even systematically looked for other examples of sequences that have both of these properties, but not the span n property. Therefore, not M sequences. In my very first report at the Martin Company on shift register sequences, it was a little report called Remarks on Orthogonal Sequences that appeared in 1954. I asked the question naively, what are all of the balanced binary sequences with 2-level autocorrelation? And at the time, I knew of the M sequences and also of what I called the quadratic residue or Legendre sequences, and I didn't know at that time of any others. I had actually suggested to my advisor at Harvard, David Witter, that this might possibly be a thesis topic. And very fortunately for me, his answer was, oh, this is just combinatorial stuff. That's all mathematically trivial. Maybe an honors thesis for an undergraduate, but certainly not a PhD thesis. because this problem is still unsolved. I wouldn't want to have spent the last 50-some years still trying to finish my thesis. An equivalent way to formulate this, which I didn't know in 1954, but realized maybe a year or two later, this is equivalent to finding all the cyclic dk lambda difference sets with the parameters v, the period being 4t minus 1, k being 2t minus 1, the number of elements in the difference set, and lambda, the number of agreements among cyclic shifts of the difference set being equal to t minus 1 for any t greater than 1, I guess. And these things are also called cyclic Hadamard difference sets. And a conjecture that I mentioned to Bellmer thought it was too flimsy to have my name associated with it at the time, so he lists this conjecture in his book and doesn't attribute it, I think fortunately at that time, is that for such a cyclic dk lambda difference set to exist, V seems to require being of one of three types. That either 4t minus 1 is a prime, or it's a product of twin primes, where p and p plus 2 are both prime, or that v is 1 less than a power of 2. This seems like a very strange set of positive integers, and that's why I thought it was a dubious conjecture. Nearly 40 years later, I'd say this conjecture is starting to look pretty good, simply because so many searches have been done and no examples have been found that are not of one of these types. So here's a summary of the constructions that we now know of for cyclic Hadamard difference sets. And the easy case, so to speak, is when V is not 1 less than a power of 2. And all the known examples there come from three constructions. One is the quadratic residue sequence or Legendre sequence construction whenever V equals 4t minus 1 is a prime number. For a subset of these primes, there's a second construction due to Marshall-Hall if this prime is also of the form 4a squared plus 27. And I would conjecture that there are infinitely many primes of this sort, but any expression that involves a quadratic term, and you think there are infinitely many primes, is beyond what number theorists have currently been able to prove. But anyhow, for all primes of this type, Marshall-Hall found a family that is based on sixth groups or sextic residues modulo the prime. And the third example, first found by Stanton and Sprott, independently by the late Al Whiteman of the USC Math Department. And the Stanton and Sprott paper, when I read it carefully, merely said that this was a construction for Hadamard sequences, but they didn't observe the cyclic property, which was explicitly observed in Whiteman's paper, that when you have a period which is a product of twin primes, you can use something very similar to the Legendre sequence, the generalization to composite cases. It's called the Jacobi symbol, and you get these cyclic shifts of the sequence of period p times p plus 2, which also has two-level autocorrelation. And very extensive computer searches have failed to find any other examples when the period is not 1 less than the power of 2. I think almost all cases have been searched at least up to v equals 10,000. So then we get the more interesting case when the period v is 1 less than a power of 2. What's happening here is that you're really looking at constructions that come from the finite field of 2 to the n elements. And that's a very rich source of examples, all of which in some way or another can be related to the trace function that maps elements of the large field, 2 to the n elements, down to the small field of 2 elements. So first of all, we know of the M sequences for all n greater than or equal to 2. These go back in the literature to the 1930s under the name of Singer difference sets. Then you have the quadratic residue sequences when 2 to the n minus 1 is also the prime. Primes of this form in the literature are called Mersenne primes. We know enough Mersenne primes now to have a plausible conjecture that there are infinitely many of them, but when we look at things as reasonable as that there are infinitely many twin primes, the proof that there are infinitely many Mersenne primes is nowhere on the horizon at all. But anyhow, this should occur probably infinitely often. On the other hand, if you restrict it to Hall's sextic residue sequence construction, when this Mersenne prime also has the term 4a squared plus 27, it's been shown that there are only 3 such primes that are 1 less than the power of 2 in all of this form. Those are b equals 31, b equals 127, and b equals 2 to the 17th minus 1, 1 to the 1071. So this is a very small family containing a grand total of 3 examples. The first new construction, sort of beyond these, was the Gordon-Mills-Welch construction, and I believe this resulted when they did an exhaustive search of period 63. And the only previous examples they were expecting were the M sequences, but they found there were some others, and n equals 6 is the first composite number bigger than 4, and what they discovered was that in taking the trace mapping from the 64-element field down to the 2-element field, there are some intermediate fields, like the field of 2 to the 8th elements, or the field of, I'm sorry, the field of 2 squared elements, and the field of 2 cubed elements. And by taking relative traces from the biggest field to an intermediate field and then to the smallest field, you could get examples that were not M sequences, and these examples are called GMW sequences. They exist for all composite n greater than 4. And in their original paper, they described pretty much all of the generalizations that have been independently rediscovered by later people who hadn't looked at the original paper that carefully. About 10 or 12 years ago, it was found that you could find certain 3-term sums and 5-term sums of decimations of M sequences. In other words, difference that the sum of 3 different M sequences at the same period, or the sum of 5 different M sequences at the same period, where we're taking every qth term, q first term, q second term, for very specific values of q, and adding them to get new sequences, produce 2-level correlation sequences. And there's also Claudio Casami's power function construction that's also similar in some ways to these constructions. And then Lloyd Welch and Guang Gong defined ways of transforming some of these earlier examples to get new examples, in particular for the 5-term sequences. We definitely do get new examples in general. And again, this is based on trace mappings. The original discovery here was that for all of the 2-level correlation sequences of period 255 to the 8 minus 1. A complete search when that was done by my former doctoral student, O.J. Cheng. And in addition to the two expected examples, the M sequences and the GMW sequences, he found another pair of examples. And in looking at that pair of examples, Lloyd Welch found a transformation that would take one of them into the other. And in his original version of that transformation, it required that the degree n had to be even. Dr. Gong generalized that construction to also cover the case where n is odd, and that turns out to be a very useful way of getting new examples from certain earlier examples. Then what are called hyperovals in combinatorics, hyperovals in projective geometries. It turned out that these led to 3 new families of two-level correlation sequences that collectively are called hyperoval sequences. Of these 3 new types, one are called Segre sequences, and then Glynn type 1 and type 2 sequences. And details of all these constructions, including variant constructions that lead to the same sequences, can be found in the book that Guangdong and I finally completed and published in 2005, Signal Design for Good Correlation, Cambridge University Press. Now, in looking for all the two-level autocorrelation sequences at period 2 to the n-1, exhaustive searches have now been completed for all the cyclic Hadamard different sets of these periods for n of 10. Starting at n equals 5 in the early 1950s, one new value of n has been successfully searched in each succeeding decade. The 10th minus 1 was really done by my doctoral student, Peter Golomb, nearly 10 years ago. So if this succeeding decade process holds up, maybe it's nearly time for someone to be able to search n equals 11. The magnitude of the search increases by 2 or 3 orders of magnitude each time you increase n by 1. Peter Golomb had to find a very clever way of almost redefining the problem to make the case searchable at n equals 10. Now, prior to the n equals 10 case, every time someone did a complete search at a new value of n, they found examples that were not previously explained. But by the time the n equals 10 search was done, basically all the constructions that I just listed were known, and the many, many examples that were found at n equals 10 all belong to categories that by the year 2000 were already known. So that leads to the conjecture that all the constructions that yield these cyclic Hadamard difference sets or two-level autocorrelation sequences of periods 2 to the n minus 1, that all of these are now known. John Dillon and the late Hans Dobrovic, I believe, were actually working on trying to prove this. They proved a number of other interesting things, including the validity of all of the previously mentioned constructions. Some of those proofs have been incomplete before their fairly recent work, but to prove this conjecture was not something that they were able to do. I'm not entirely sure that I believe this one. I would have to see the results of the searches at n equals 11, and perhaps more interestingly at n equals 12, which is a composite number, and maybe even at n equals 13, which is the next Mersenne prime exponent. And if none of those turn up any new examples that we don't already know, then I would almost certainly believe this conjecture, but without additional data, somehow n equals 10 does not impress me as being a huge number. I would say this is a conjecture based on very limited data. That's all that I had prepared for my slides, but I did think that if I have time, which I do have a little of, I would mention their conjectures about nonlinear sequences like the de Bruijn sequences. And by definition, a de Bruijn sequence is a sequence of period 2 to the n, where every vector of length n occurs exactly once, including the all zeros vector. But if you delete a single zero from that run of n zeros, you get what I defined earlier as the span n sequences, and they're in trivial 1-1 correspondence with the de Bruijn sequences. And you can get all of those sequences from a